So welcome to another installment of Intermolecular Forces, Influence on Physical Properties. In this case, we'll be looking at boiling and vaporization and vapor pressure. So it should be no surprise to you at this point that molecules in a liquid are always moving. You have vibrational and then rotational and translational movements. So rotational movements are the molecules kind of spinning, and translational are where they go shooting off. Where they go shooting off all over the place. So maybe that's where they're moving this way like that. Okay. We gave you a definition of the average kinetic energy. And average kinetic energy is calculated by looking at constant times temperature. It's related to that. But what I want you to know, and this is the part this is saying, that if you were to look at a distribution of molecules and see how, you will find out they don't all have the same kinetic energy. There's an average kinetic energy, but some of the molecules have more than the average energy and some have less. So let me show you a plot I found and then kind of manipulate it a little bit. And this will kind of point out what I'm trying to say. So here's a plot. And what you're going to see is we have the number of molecules versus kinetic energy of each, of the molecules. And so this represents a population. So most of the molecules actually will, in this particular plot, fall below the average kinetic energy. So if you take all the molecules and you average them, you'll get something in this range. This was actually computed. I pulled it off of the internet where someone had actually simulated it. I just changed the axes and labeled things. They had everything in terms of math. And so I just replaced it with more meaningful to you kinds of things. So the point is, some of the molecules have a lot of extra energy compared to others. And so at the average energy, you have some on this side of the average energy and some with greater average energy. So that means that some molecules may have enough energy to break free of the intermolecular forces that hold them together as a liquid. And that's what happens during evaporation. Some of the molecules have enough energy to bust free and go off and become a gas. But most of them don't at a given temperature. And if I were to increase this temperature, what you would see, let's say this is my increased temperature, I would have a different distribution. The average kinetic energy, would move. I drew this curve. It may not look like that. But anyway, the point is the average kinetic energy would move to a higher level at a higher temperature. And that's something we've been saying all along. You increase the temperature, you increase the average kinetic energy. All right. In another video, I showed you a simulation where we showed how the molecules move as a function of temperature. So remember, as we increase the temperature, the average kinetic energy increases. And what I want you to, I'm going to point it out again, but I'm going to show the simulation, just the small part of it, and you're going to see these molecules. Every now and then there's going to be a population of molecules at a given temperature that has a little more energy than the rest of them, and it's able to pop free and go up into the gas phase. And so I'm going to let that play right now, and you can see it's moving around, and every now and then you'll see as the temperature increases, you're going to see molecules getting more energy and springing forth, and you can see them leaving. And as the temperature gets higher, more and more population have enough energy to break free, and that's what evaporation essentially is. So I just wanted you to kind of see that simulation again and apply the concept that I just mentioned. And this really is just a static picture showing the same thing. And so there's a couple of things that factor in here. I hit the wrong button here. One of them is obviously the temperature. The greater the temperature, the more molecules there will be that will have more energy to break free of all the intermolecular forces holding them together. The other thing is if you have a greater surface area, then there's more opportunity for these molecules to get to a phase boundary. In this case, the phase boundary would be liquid and gas, to make that jump. So evaporation, of course, would happen faster if you had more of a surface area to where these molecules could interact. Now, as these things bounce up, that creates a vapor. And eventually, when there's enough kinetic energy, we'll see that we actually reach a point of boiling, and that vapor increases to a point where it begins to just do a phase transition rather than just a little bit of evaporation every now and then. It becomes all out boiling where we go from a liquid to a gas. Now, the opposite of vaporization is condensation. That's where the molecules of vapor condense. You cool them down enough and they will condense and form a liquid. And so think about it. If you take a gas and you lower the temperature, the molecules slow down, and when they do collide with one another, they may stick because they have at lower temperatures, they have less and less kinetic energy, and the forces of attraction that can hold the molecules together can start to influence that phase change. And that's what we call condensation. So here is a video that I think you may find interesting. So in this video, I have a metal can up here, and I'm pouring in liquid nitrogen, which is here. Liquid nitrogen is about, say, 100, sorry, let me put this in red so you can see this better. About minus 195 degrees Celsius. And if I can cool the outside of this canister to that level, then what will happen is the oxygen from the air will bump into that metal and experience a temperature that's actually below the boiling point of oxygen, and I should get a condensation of oxygen that will start dripping. And so if we're lucky, we'll see the drip. So let's see if this works. Okay, here we go. Now it's cooling off, and I'll try to point out when I start seeing it. It's cooling off and the air is starting to collide with it, and before long, pretty soon, right in this region, you should start seeing some dripping. And there it is. See that dripping right next to the dot just to the left? That's actually liquid oxygen dripping into this container. And so that's a great example of how if you cool down even a gas that you normally don't think of as a liquid, like oxygen, I can actually make liquid oxygen. And I collected some here, and then eventually I torched it. Used it to torch a Cheeto. But that's kind of what I wanted you to see. You can kind of see something. By the way, not many people get to see oxygen with their own eyes, and you just did. But that's an example of condensation. Lower the temperature enough so that the intermolecular forces of attraction between the molecules can start hooking them together, causing them to stick and form a liquid. So vaporization or evaporation and condensation are opposite processes. Liquid going to gas, gas going to liquid. And honestly, they happen at the same time. It's just that in an open container, once you get a liquid that, if I draw a little container here, okay, once we get a liquid, I'll put in blue to remind us that it's a liquid, the liquid jumps into the gas phase and just keeps going because it's an open container. So it gets diluted, if you will, and spreads out and doesn't really come back and recondense, because there might be one that moves around and comes back in, but there's way more of a concentration of water or liquid here and much less of a concentration out there. And so the net effect is that the rate of evaporation is far less than the rate of condensation, and so there's a net loss of liquid. And so that's why eventually, if you leave a cup of water out or whatever over time, it's going to disappear. But if you leave the cap on, that's a different story. Now, the vapor is not allowed to spread out indefinitely. What eventually would happen, let's say we have another case like this. We have another container, and this time we'll have a lid on it. So this, I'm just going to write lid so you know that it's a closed container. Then what's going to happen is the molecules of the liquid are going to pop up until they reach a final concentration of gas above the liquid, and then you're going to start seeing that in that case you can get condensation happening as the liquid comes back down. And so essentially what will happen is you'll have some things moving up, some things moving back down. And that leads to a very interesting situation where the rate of vaporization and condensation will be the same. Under that condition, we have something called a dynamic equilibrium. And the vapor above here, the amount of vapor that's above the liquid does not change. Equilibrium. It stays constant. So, as you may have guessed, intermolecular forces of attraction then play a role in evaporation and condensation. It turns out that you could probably reason this out by now. You're getting the idea that the weaker the attractive force is, the easier it is for molecules to be released. So the weaker the attractive force is, the less energy they need to vaporize, so they'll be more volatile. They will turn into vapor more readily. And so when you have a situation like that, where the net result, well, you'll have more molecules in the vapor phase than if you had stronger forces. So weaker forces will lead to greater amounts of molecules in the vapor phase. Stronger forces, just on the opposite, will have less molecules in the vapor phase because they're held more tightly. Okay? And so liquids that we say evaporate easy, that's, you know this word, I'm sure, volatile. And those that don't evaporate easily are non-volatile. So the non-volatile liquids have pretty high forces of attraction holding it together. The volatile ones, the ones that evaporate really easily, those have weaker forces of attraction holding them together. Now here's a word from the past, endothermic. You've seen it in Chemistry 111, or wherever you took it, whatever the first semester of Gen Chem is called, you learned about endothermic process. Endothermic processes are those that require heat. You may remember the old delta H. Okay, delta H is enthalpy, change in enthalpy, and that's an energy. When the change in enthalpy is positive, that means energy was consumed by the process. That's called endothermic. When delta H is negative, has a negative sign, energy is released, and that's called exothermic. So that should be a review from General Chemistry 1. Okay, so endothermic means heat's required. So this kind of makes sense if you think about it. When energy is consumed by or used, absorbed by a liquid, the molecules gain more kinetic energy and can break free and vaporize. So it actually takes heat, which makes sense because if you think about it, you want to boil something, you want to turn it into a gas, you got to put heat to it. So vaporization requires heat. Condensation releases heat. So vaporization has a positive delta H, whereas condensation has a negative delta H. Heat is released for condensation, so it's exothermic. So just think through that for a little bit. That will make sense if you think about it. If you're going to, in the example I just gave you, I added a very cold substance, which is going to take the energy from the molecules that hit that container, so that the molecules, when they hit that container, are going to release their energy into the liquid nitrogen that I used. And so that's exothermic. They release their energy. Whereas when you heat up a liquid, the energy is absorbed. And that energy gets converted into kinetic energy, which can bust free from the intermolecular forces that hold them together. So now that we realize that evaporation or vaporization is endothermic, it requires heat in order for it to happen, we can now, and I just reminded you about enthalpy, delta H, we can now define something called the heat of vaporization, or the enthalpy of vaporization, delta H vap. For vaporization, which is endothermic, delta H vap is a positive number. When condensation occurs, delta H turns into a negative number. But the number itself is the same, it's the sign that changes. So let's look at this. So for water, the delta H of vaporization is 44 kilojoules per mole. The delta H for condensation, so if I go ahead and write this, I could put another little column in here. I can say delta H for condensation is minus 44.0 kilojoules per mole. So you just simply add a negative sign to these values if you want to know what the delta H of condensation is. So you can kind of see there is that relationship. But delta H for vaporization is always a positive number. Delta H for condensation is always a negative number. And this is how the two are related, simply by putting a negative sign in front of vaporization. That will give you delta H of condensation, and that's what I kind of just demonstrated here. So I referenced this a little bit earlier about this thing I call dynamic equilibrium. In a closed container, okay, what happens is the vapor builds up until it reaches a point where the rate of vaporization is equal to the rate of condensation. When that happens, then there is a fixed amount, so I'm going to draw my little jar again. When that happens, there's a fixed amount of vapor particles, and that stays constant when the rates of vaporization and condensation are equal. At that point, when they're equal, we say that the process is in a dynamic equilibrium. Evaporation and condensation are both happening in that, there'll be evaporation happening, but in an equal way in terms of rates, the condensation's also happening at the same time. So the net effect is that the little molecules of vapor, even though a particular molecule may go back up and come right back down, when you count all the molecules themselves, though, that amount stays constant. When that's the case, this is where we're at something called dynamic equilibrium. It's dynamic in that molecules are still being released and condensed constantly, but the net effect is the vapor is all, the number of vapor particles are all the same. Now here's just another similar way to look at this. You can measure the rate of evaporation is going to be consistent, okay? Because the rate of evaporation is going to be fixed because you have the concentration of your liquid. Even though you're losing molecules, the concentration of your liquid remains the same. You just lower the volume, but the concentration's the same. And so because of that, the rate of evaporation remains constant. But as you start building up molecules, you hit a point where the rate, now the rate's over time increasing of condensation, and when you get enough vapor particles up in the above the liquid, they start coming back down at faster and faster rates until they equal the rate of evaporation. At that point, both the rate of condensation and the rate of evaporation remain constant. And that's when we're at this dynamic equilibrium. And this kind of shows a similar thing again. You can start seeing initially you get molecules of gas start popping up until they start building up. Eventually, when you get enough of these above the solution, the rate of condensation equals the rate of evaporation, which is the definition of dynamic equilibrium. Here's where it starts getting fun, in my opinion. Now we can talk about vapor pressure. And vapor pressure is really the pressure that's exerted by the gas phase of the liquid that's above the liquid. And you dealt with this back in Chem 111 again, because you even did an experiment, if I remember correctly, and I'm pretty sure I am right. You actually did an experiment where you collected a gas over water. And the problem was the water had its own vapor pressure at that temperature. If this is water, I'll just call this water. You had some, and you have a closed container so the vapor can't get out. You build up till you have a dynamic equilibrium, and you have a certain concentration of water molecules in the gas phase, and that concentration remains constant. Okay? Now, let's remind you of another little cute thing you know about. PV equals nRT, the universal gas law. And so we can rearrange this, so now you get I divide both sides by V, and I can just divide N by V. Mathematically, it's the same as if I divided the whole thing by E. But at a given temperature, this part becomes constant. This part is concentration. N is moles, volume would be liters, so moles per liter, that'd be concentration, molarity. So you can express the concentration of the particles in terms of a vapor. And that, I mean, in terms of a pressure. And that's what vapor pressure is actually telling us. It's giving us a sense that how many particles of gas do we have above that. Now you can imagine, as everything we've been saying, and I'll risk repeating myself over and over again, because actually I think that that's a helpful thing to do when you're learning something, that the weaker the forces in the liquid that's holding the molecules together, the higher the vapor pressure, the more particles there will be above the liquid. If we're comparing two liquids and one has hydrogen bonding and the other one has dispersion forces, we would expect the one with dispersion forces to have more gas particles above the liquid than the one with hydrogen bonding. Okay, so the weaker the attractive forces, the higher the vapor pressure, and vice versa. There's your vice versa. The higher the vapor pressure, the more volatile the liquid is. So if something has a really high vapor pressure, that means that the molecules aren't being held together very well, and they're readily becoming a gas. So that's what we mean by vapor pressure. And this part will kind of trip you up, because I think people down the road, they get this mixed up, because it turns out that things that have a high vapor pressure, and I'm kind of getting ahead of myself, but I'm going to mention it here. Things that have a higher vapor pressure have a lower boiling point. It takes less of a temperature to give them the energy to break free and boil. So higher the vapor pressure, the lower the boiling point. And that's something we'll see again, but I just thought I would introduce it here, since boiling is actually very related to evaporation and vapor pressure. And really this part, I think, is just to help you realize that this is an ongoing process. If for some reason, let's say you had a piston, okay, something just happened here. Let's say you had a piston, and that piston looked like this, okay, and you had the piston set here, and then say here's a liquid, here's your vapor, your gas, and you have the piston here, and it has a fixed volume, and you let this thing reach to the dynamic equilibrium, and then you have your liquid, your gas, but you move the piston up and you increase the volume. Well, by increasing the volume, you're diluting the number of gas particles, and so for a moment you're going to have more evaporation, higher rate of evaporation, until you reach the vapor pressure for that liquid again, and then you'll reestablish the dynamic equilibrium. That's what this is saying. All this stuff here is saying that. So the point in bringing all this up is, no matter what the volume is, once you reach dynamic equilibrium for a liquid at a given temperature, it's going to be the same. So vapor pressure at a given temperature, I'll just say vapor pressure, VP, at a given temperature, okay, is constant, no matter what the volume is, once the dynamic equilibrium is reached. So I'll say regardless of volume. and I'll just say V for volume, once the dynamic equilibrium is reached. And that's a concept that you'll have to reckon with, and we'll keep coming back to it because it's actually pretty important. Here's the same thing I just showed you. Here's the piston experiment. Okay, if you play around with the volume above the liquid, you're going to get changes in rates of condensation. You know what? I just realized something. I originally say that the rate of evaporation changes, but no, I'm talking the rate of condensation changes when you change the volume. Okay, so when I change the volume, the rate of condensation will change accordingly. So in the case of when I dilute, make the volume bigger, the rate of condensation is smaller until dynamic equilibrium is reached, and then you're back at this situation. And same thing, if I shrink the volume, in that case, the rate of condensation increases instead of decreases as it did in that case. So it increases in this case until, again, the vapor pressure is established, and then it's both hit that dynamic equilibrium again. And so, as you may also guess, so I just said vapor pressure is influenced by the strength of the intermolecular forces of attraction. The stronger the intermolecular forces of attraction, the lower the vapor pressure, and vice versa. Temperature will increase. As the temperature increases, the vapor pressure increases, and I think you could figure out why. You're giving, as you increase the temperature, you're giving the molecules more energy to break free and join the vapor phase. And so you'll build up that pressure as a result. If you lower the temperature, guess what? Vapor pressure goes down because you slow down the molecular movements. The kinetic energy is lower, and so it has less energy to break free from the liquid phase. So that's pretty much something we've been seeing, just like with viscosity and surface tension. You have to consider both temperature and the strength of the intermolecular forces to really understand what's going on. The general idea, though, is that temperature opposes the intermolecular forces of attraction. As you increase temperature, you can overwhelm the forces of attraction holding the molecules together, and that can lead to more vapor. So that's kind of the end of this section. The next section that we cover, we'll get into how to do the calculations where you kind of look at the quantitative relationships between vapor pressure and temperature. And that's something called the Clausius-Clapeyron equation, and we will deal with that next in the next section.